Okay, continuing on with working with determinants. Okay, there is yet another approach to finding out solutions to an equation system, and we have what is referred to as Cramer's Rule. And we have just a general model, okay, where we have for a two equation system, and we have, so we have the coefficients. Okay, we have a of 1, 1, x of 1 plus a of 1, 2, x of 2 is equal to b of 1. And then we have a of 2, 1 times x of 1 plus a of 2, 2 times x of 2 is equal to b of 2. And we have for the solution, looking at solving for x of 1. Okay, so we have b of 1 times a of 2, 2 minus b of 2 times a of 1, 2. All over we have a of 1, 1 times a of 2, 2 minus a of 2, 1 times a of 1, 2. And we have for the other variable to solve, we have with x of 2. So this time we have taking the difference of the product of b of 2 times a of 1, 1, and what we have with b of 1 times a of 2, 1, and we have divided by the same denominator. Okay, and this will consist of defined solutions as long as the denominator that we have here does not equal to 0. And a determinant can represent each numerator and denominator in the solution as shown below. Okay, and so we have for x of 1, 1, just putting this in terms of 2 by 2 determinants. Okay, so we have the determinant of b of 1, a of 1, 2 at the top, and then we have b of 2, a of 2, 2 in the second row of the determinant in the numerator, and we have all over what we have with the determinant resulting from what will be referred to as the coefficient matrix, and we have with x of 2. Okay, so you have a of 1, 1, b of 1, 1, a of 2, 1, b of 2, all over, again, the same denominator. And we will have solutions to both x of 1 and x of 2 just as long as we have the determinant of what we have in the denominator to be non-zero in value. And looking at what we have, again, so just a way of looking at this, so we can have what we have for x of 1. Notice we have with the terms in the numerator. We can say that's going to be referred to as the determinant of a of 1. And for x of 2, what we have in the numerator, we can say that's going to be the determinant of a of 2. And we'll get, again, into specific numerical examples. But we have, in short, we have x of 1 is equal to the ratio of the determinants of a of 1 with respect to a, and we have x of 2 to be the ratio of the determinant of a of 2 with respect to that of a. And just like the minors and the cofactors, there will be a bit of a cover-up method that is involved. And let's say that if we're looking at solving each system by Cramer's rule, and we'll say that we have 3 times x of 1 plus 4 times x of 2 is equal to 25. And also x of 1 minus x of 2 is equal to negative 1. So we're looking at the values of both x of 1 and x of 2 that will belong to both equations in the system. Now, you're going to have a coefficient matrix A, and this will be the coefficient of the x of 1 and x of 2 terms. And so we have with this, okay, so you have like 3 and 4, 1 and negative 1. And if we look for the determinant, okay, so we have 3 and 4 at the top, 1 and negative 1 on the bottom. And the value of the determinant of the coefficient matrix, okay, is going to be negative 7. Now, looking at what is referred to as a of 1, and this will be the backdrop to determining the value of x of 1. And again, notice we had 4 and negative 1 to be in reference to the coefficients of x of 2. And creating the backdrop to solving for x of 1, what I'm going to do here is I'm going to find the determinant of a of 1. So I'm going to replace the coefficients of the x of 1 terms with the constants to which each equation will be set equal. So in lieu of 3 and 1, I'm going to have 25 and negative 1 in place. And for the determinant that is formed, we have 25 times negative 1 minus the product of negative 1 and 4. And so we have negative 25 and what's going to be the addition of 4, where we have negative 21. Now for the determinants of a of 2, I'm going to replace the x of 2 coefficients with 25 and negative 1. Okay, so another cover-up type method. So we're going to have 3 and 1, again, the x and 1 coefficients, and again, replacing the x and 2 coefficients with the constants to which each equation is set equal. So I have 25 and negative 1, and taking that determinant, we have 3 times negative 1 is negative 3, and we have minus 1 times 25, which comes out to negative 3 minus 25, and so we have negative 28. And so we have for x of 1, this will be the ratio of the determinant of a of 1 with respect to that of a. So we have negative 21 over negative 7, so x of 1 is equal to 3. And for x of 2, we have the determinant of a of 2 with respect to that of a. So we have a negative 28 to negative 7 ratio, which simplifies to 4. So x of 1 is 3 and x of 2 is 4, and both of these values will work in these equations. And now let's say that if I had the equations in the sort of perhaps more orthodox x and y layouts, and let's say that for this system, if I have negative 10x plus 4y is equal to 25, and 2x minus 3y is equal to negative 1. And looking at what we have here, if I go back, to finding out what the determinant of the coefficient matrix will be. So I'm looking at the coefficients of the x and y terms. So we have from the first equation, I have negative 10 for x, 4 for y. Second row, I have 2 for x, negative 3 for y. And taking the determinant, so again, I have negative 10 times negative 3 is 30, and I have minus 2 times 4, whereupon we have 30 minus 8 comes out to 22. So the determinant of the coefficient matrix is equal to 22. And looking at solving for the determinant of a of 1, so we're going to replace the negative 10 and 2 with 25 and negative 1. And in the process, so we have 25 times negative 3 is negative 75, and we have minus negative 1 times 4, and this will translate to negative 75 plus 4, which will be negative 71. And if I look for the determinant of a of 2, which will be the backdrop to determining what y is going to become, so I'm going to replace 25, I should say replace 4 and negative 3 with 25 and negative 1. And so we have with this particular determinant setup, again, we have negative 10 times negative 1 is 10, and we have minus 2 times 25, which is negative 50, and 10 minus 50 comes out to negative 40. And so for x, in this case, we have the determinant of a of 1 over the determinant of the coefficient matrix. And so we're going to end up with a non-integer amount where we have minus 71 over 22. Now for what we have in the case of y, so you're looking at the ratio of the determinant of a of 2 with respect to the determinant matrix A. And so we have negative 40 over 22, which simplifies to negative 20 over 11. Okay, looking at expanding the model. Say we have a 3-equation system whereupon we have x plus y plus z is equal to 9, and 3x minus 2z is equal to 8, and we have 2x minus 4y is equal to negative 4. And we can say that for establishing the coefficient matrix A. Okay, so we have for the first row, we have 1, 1, and 1 in reference to 1x, 1y, and 1z. Middle row, we have 3, 0, negative 2 in reference to 3x, 0 since we don't have a y term present, and we have negative 2 for the minus 2z. And for the last row, we have 2 for 2x, negative 4 for 4y, and 0 since we don't have a z term in this last equation. And for the determinant of this coefficient matrix, again, just looking at the sign changes among the cofactors and the minors. Okay, so you're looking at plus 1 times the determinant of what we have with the coefficients or cofactor and minor first row, first column, where we have exposed 0, negative 2, negative 4, 0, and then we have minus 1, and we have with the minor of what we have with the first row, second column, we have the exposed elements, 3, negative 2, and 2, 0, and we have plus 1, and we have for the exposed elements, we have 3 and 0, 2 and negative 4, and so we got 1 times negative 8 minus 1 times what's going to be positive 4, and we have plus 1 times negative 12. So the value of the determinant of this coefficient matrix A will end up at minus 24. Now for the determinants of A of 1, again, if I replace 1, 3, and 2 for x with 9, 8, and negative 4, and going through the same process, we're going to end up with the value of the determinant of A of 1 to end up at minus 96. And for what I have for A of 2, again, replacing the y term coefficients with 9, 8, and negative 4. So replacing what I have, again, with what was originally 1, 0, negative 4 with 9, 8, and negative 4, and following through in the same fashion, we have the value of this determinant to come out to minus 72. And for the z-term coefficients, okay, looking for the determinant of A of 3, so replacing the 1, negative 2, and 0 with, again, 9, 8, and negative 4, and following through in the process, and the value of this determinant comes out to minus 48. And so this time around for x, this will be the ratio of the determinant of A of 1 with respect to that of the coefficient matrix. So we have negative 96 over negative 24 to come out to 4. For y, I have the determinant of A of 2 with respect to that of A. And for this ratio, I have negative 72 over negative 24, which is 3. And for z, I have the determinant of A of 3 over the determinant of A. So we have a negative 48 to negative 24 ratio, and that simplifies to 2. So we have for the unique solution, we have x equal to 4, y equal to 3, and z equal to 2.